Hey everyone, welcome to Quesadilla Math with me, Mr. Padilla. Today's topic is matrices and how to perform operations on them and with them. So, let's get started. So, matrix algebra is a field of study that uses what are called matrices to apply to a whole bunch of different kinds of fields. They're used a lot in physics and in all the various branches in physics. You can find matrices being used in computer science and, of course, just in pure math. So, let's talk about what matrices are. So, a matrix is a rectangular array of elements. Usually you'll see numbers being the elements here, but you can also have variables and different things being elements of the matrix. Arranged in rows, which are horizontal, and columns, which are vertical. We call these rows and columns the dimensions of the matrix. In this case, we're looking at a 3x4 matrix because we have 3 rows and 4 columns. These numbers typically represent values in a system of equations, which we're going to be learning how to use in another video. But for now, let's get more into the basics of different parts of a matrix. The different numbers that you can find in a matrix are what we call entries. So each one of these numbers is an entry of the matrix. To be able to give each entry kind of a location or a position, we use this is a system using the rows and the columns to figure out where each entry lies in the matrix. So here you can see that it goes by row then column. So we would call this entry A11, A12, A21, A22. So if we were to be asked a question, what is the value of A23? You would look at row 2. So we'd look here in row 2, column 3. So it's the position row 2, column 3, almost like a coordinate. And if we were looking at A31, that would be row 3. So this is row 1, 2, 3, column 1. So it would be 9 in this case. So now let's talk about some of the different operations that you can perform on and with matrices. First thing we'll talk about is how matrices can actually be added and subtracted with each other just like real numbers can. There is a catch though. In order to be able to add two matrices together, they must have the same dimensions. They have to have the same amount of rows and columns, same dimensions. And when you add matrices together, what you're really doing is adding the corresponding elements, the same entries in each one. So let's take a look at our first example. Here we have matrix A, which is this two rows by 3 column matrix. And we also have matrix B, which is again a 2 row and 3 column matrix. So these are both considered 2 by 3 matrices. So since they have the same dimensions, they can be added together. So to add these two matrices together, if we're going to add matrix A with matrix B, we're really just adding the corresponding elements. So we're going to add A11 with B11, A12 with B12, and so on. So in this case, we have 1 plus -3, since these are both in row 1, column 1. 1 plus -3, then 5 plus 9, -2 plus 7, -3 plus 5, 0 plus -12, and 3 plus 4. So simplifying our sums gives us -2, 14, 5, 2, -12, and 7. The sum of matrix A and B gives us this other 2 by 3 matrix. Notice that when you add two matrices together, the sum matrix should also have the same dimensions, 2 by 3. So in our next example, we have matrix A, which is a 2 by 2 matrix. Since it has 2 rows and 2 columns, we actually refer to this as a square matrix. And B is a 3 by 2 matrix, 3 rows and 2 columns. So if we were to try to add these two matrices together, we wouldn't be able to, because we wouldn't be able to add corresponding entries together. We could add 3 plus 6, -1 plus 1, -4 plus 1, and 11 plus -5, but we would have nothing left in matrix A to add with matrix this last row of matrix B. So therefore we say this is undefined, and we really would say that we cannot add these matrices at all. Subtracting matrices is pretty much the same process, except this time you're subtracting corresponding entries. So here we're subtracting matrix B minus matrix A. So we're taking -3 minus 1, 9 minus 5, 7 minus -2, which is actually adding, 5 minus -3, -12 minus 0, and 4 minus 3. Simplifying all of our sums, we get -4, 4, 9, 8, -12, and 1. So we can also multiply our matrices by a regular number, which we call a scalar. And we call this scalar multiplication. The scalar is the fancy name that we give this regular number. And what it does is when you multiply a matrix with a scalar, you're multiplying every entry of that matrix with that scalar. It really is a pretty simple process. In example 4, you can see that we multiply -5 times this square matrix, 2 by 2 matrix. So we're going to multiply -5 with each of the entries. -5 times 6 gives us -30. -5 times -9 gives us positive 45. -5 times 8 gives us -40. And -5 times 3/4 gives us -15/4. Yes, you can have fractions in a matrix. In example number 5, here we're multiplying by a fractional scalar, this time a rational number, and it works the same way. 1/2 times 8 gives you 4, 1/2 times 3 gives you 3 halves, 1/2 times -2 is -1, and 1/2 times 12 is 6. Now, multiplying two matrices together is a little bit more complex than multiplying by a scalar or addition and subtraction. In fact, matrices can only be multiplied together if the number of columns in the first matrix is the same as the number of rows in the second matrix. Which means when you actually write out your matrices, if you write down the dimensions, you'll notice that the two inside numbers will match each other. In this case, we have a 2 by 2 multiplied with a 2 by 1 matrix. So the number of columns in the first matches the number of rows in the second, so we can multiply these two matrices. If we were to flip these, then what you have is a 2 by 1 times a 2 by 2, and since the middle numbers, the inner numbers, don't match, you wouldn't be able to multiply these two matrices in this direction. So in this case, these two matrices, you can only multiply them in this way, not the other way, which of course we call the commutative property of multiplication, which doesn't apply to matrices. Now, to actually multiply your matrices, there is a special trick to it. When you multiply them, what you actually are doing is multiplying a row times a column. But what you're doing is you're adding the products of corresponding entries. So what this means is that if we have our 2 by 2 matrix times our 2 by 1 matrix, 2 rows, 2 columns, 2 rows, 1 column, what you'll do is you will take the first row times the first column, which will give you A11. So your first entry will be the first row, first column. And the way you do this is by taking the first element in the row, multiplying it by the first entry in the column. So M times I in this case. Then you take the second element in the row, multiply by the second element in the column, A times X, and then you add those together, and that will become your element or your entry for that particular part of the matrix. Then you'll take the second row and multiply it by the next column. So here we have T times I, and then R times X. Add those together, and that will be entry number 2, 1, because it's row 2 times column 1. Since we only have one column in this matrix, we would have, in the end, this 2 by 1 matrix. Notice that the ending matrix has the dimensions that we on the outside of our two matrices here. So if this was a 2 by 2 times a 2 by 1, you just have to look at the outside numbers to figure out that you should end up with a 2 by 1 matrix as your product. While this is a handy way to remember how to multiply matrices, let's take a look at a few examples and get some practical hands-on experience. So in this example, we're going to be taking a look at matrix A, which is 1, 2, 3, 4, and matrix B, which is 5, 6, 7, 8. I've taken the liberty of highlighting the rows and the columns so that when we multiply these, it'll be a little bit easier to see. Now, the first thing that you need to check is, can you actually multiply these two matrices? Since these are both 2 by 2 matrices, you'll notice that the inner numbers are both 2, so we can go ahead and multiply them. We will expect to get another 2 by 2 matrix since those are the outer numbers of these. So let's go ahead and multiply matrix A times matrix B. So once again, the secret is to multiply the rows by the columns and to keep track of the location or the position for each of your entries. So we're going to take row 1 and multiply it with column 1. This will give us the entry row 1, column 1, 1, 1. So we'll take the first element in our first row, 1, multiplied by the first element in the first column, 5. Then we'll also take 2 times 7, and we'll add those. So we'll have 1 times 5 plus 2 times 7. Here you can see where each element came from. Then we'll go ahead and multiply row 1 times column 2. I usually like to go row by column and finish up the first row before I move on, but there's a lot of different ways you can do this. So in this case, I'm going to multiply 1 times 6 plus 2 times 8. Then I'm going to take row 2 and multiply it with these two columns as well. 3 times 5 plus 4 times 7. Then 3 times 6 plus 4 times 8. So now we have all of our entries set up. All we have to do is do some quick calculations, and we will find that matrix A times matrix B gives us this, again, 2 by 2 matrix, 19, 22, 43, and 50. Now let's take a look at multiplying some matrices that don't have the same dimensions. So in this example, once again, we have matrix A and matrix B, and we're going to go ahead and multiply A times B. In this case, let's note the dimensions and see if it's even possible for us to multiply. Here we have a 2 by 3 matrix, 2 rows, 3 columns, and matrix B is a 3 by 2, meaning that we can definitely multiply A times B. Now, if you were to rearrange it, you'd actually be able to see that we could actually multiply it the other way as well. However, in this case, we're going to multiply A times B, and you should also note that since the outside numbers are both 2, we should end up with a 2 by 2 matrix as our product. So once again, color coding helps make this a little bit easier to see. We're going to start by multiplying row 1 times column 1. So 6 times 3 plus 6 times negative 5 plus 3 times 4. Then we're going to take row 1, multiply it with column 2. 6 times 5 plus 6 times negative 3 plus 3 times 2. Then row 2, 0 times 3 plus 2 times negative 5 plus negative 2 times 4. Then finally, we're going to take row 2, multiply it with column 2, 0 times 5 plus 2 times negative 3 plus negative 2 times 2. You'll notice that we have essentially a 2 by 2 matrix, and all we have to do is perform the calculations, and we can see that our product A times B is the matrix with entries 0, 18, negative 18, and negative 10. Again, it did turn out to be a 2 by 2 matrix, just like we had predicted. In our last example, we'll take a look at what happens if you square a matrix and what does it mean to do that. In this case, we're going to take a look at matrix D, which is a 2x2 matrix, -3, 5, 1, and 2. So to find D squared, it's a lot of people are going to make the mistake of actually just trying to square each of the entries in this matrix, but that's once again not how this works. When you square anything, including a matrix, what it means is to multiply it by itself. So D squared really means D times D. So now take this moment and pause the video to see if you can multiply this matrix with itself. I'll give you just a few seconds. Okay, so hopefully you found that D squared, when we take this matrix D and square it, we end up with 14, -5, -1, and 9. Another 2x2 matrix. So the reason that was our last example is because there is no such thing as matrix division. There's no process that would allow us to divide two matrices in any way that makes sense. Like I mentioned earlier, there is a field called matrix algebra. And as if you're familiar with algebra, you know that division is usually a very important part of solving for a variable. In the case of matrix algebra, instead of solving for a single variable, you're usually solving for a matrix that's full of variables. So how do you do this without using division? Well, that's going to be the topic for another video. So that is the last example for today. So we will continue our lesson on matrices in another video. I hope that this was informative for you guys and will help you on your journey learning to use matrices in your algebra classes and beyond. So I will math you next time.